Okay, I finished about a dozen videos on the fundamental topic in my new series for the FRM, and now I'd like to start the series on the quantitative topic, and beginning with, I admit, terms that I am fond of because they're so central to risk measurement. And so what I'd like to show for both a continuous and a discrete random variable, and to characterize the continuous and discrete, I'm going to use a normal distribution for the continuous and a Poisson distribution for the discrete. And then I want to illustrate the three key terms that I'm saying are really central to risk measurement. That is the probability density function, also called the PDF, the cumulative distribution function, the CDF, and its inverse, which is the inverse cumulative distribution function. That's a mouthful. It's also called the Quantile function. In order to illustrate these key probability terms for the continuous random variable, of course I'm going to use the familiar normal distribution function. As a probability function, it must have two perspectives. That's the PDF and the CDF. So here for the normal, and I'm using the standard normal, in green I have the familiar bell-shaped curve centered at 0 with standard deviation of 1, and that is the probability density function. I'm sure you've read or heard how in the case of a distribution that characterizes a continuous random variable, we can't specify the probability of an exact value. And for this reason, the value here of the PDF isn't really intuitive. The standard normal happens to peak at about 0.4, but that's not really very meaningful for us because we need to look at the probability of a value falling between an interval because this is continuous. And so maybe more helpful to us is the CDF. And the CDF I like to use in uppercase because it's the integral of the PDF mathematically. So that CDF is graphed here in blue, and it is the cumulative distribution function. So mathematically, this is a key point. Again, the PDF integrates to the CDF, or its antiderivative is the CDF, and therefore the derivative of the cumulative distribution function is the probability density function. The CDF is also helpful, I think, because we want to step back here and think about functions. In math, of course, we have a wonderful supply, an infinite supply of functions. Most functions are not probability functions. What is it that qualifies a function as a probability function? Well, we can look at the short list, but there's just really one key idea, I think, and that is that we have a valid CDF, cumulative distribution function. A valid cumulative distribution function is bounded by 0 and 1 here, or 100%, because a probability, discretely or cumulatively, must be between 0 and 100%. After all, we can't have the probability of an event being something like 130%. And so you can see the normal here does have a valid, let's say that again, the normal distribution is a valid probability function because it has a valid CDF here, bounded by 0, technically asymptotic to the 0, and then up here bounded at 100%. Again, technically asymptotic to 100%. So that makes it a valid probability function. And then we necessarily have the two perspectives, the PDF and its integral, the cumulative distribution function. So I have here the standard normal is elegant because it only requires the two parameters, mean and standard deviation. If I have mean of 0 and standard deviation of 1, then I have the so-called standard normal. And then here I have three calculations that illustrate the three key terms I'm trying to illustrate or convey. And I start with small p, which stands for probability. And Excel generates then for me a uniform random variable. This is the most simple, elegant, common random number generator in the world. A random value between a continuous random value between 0 and 1. You can see each time I hit it, I get something between 0 and 1, and that small p denotes probability. Very simple. Doesn't even require parameters. Now, the p then becomes an input here into this function, which is a quantile function, or more technically, this is one of the key terms I wanted to convey. This is the, right here, this is the inverse cumulative distribution function. Because, notice it's got f raised to the -1, because the inverse cumulative distribution function is the opposite of the cumulative distribution function in the sense that it accepts the probability as an input and returns for us the z value, or really the quantile. So the z value here is the x-axis. You can see I have the x values here. I could also have called this z. I could have labeled this as z, but the z just connotes it's the normal distribution, and we can call these distributional quantiles. And so here in this case, I'll run one more random variable, see if I get a higher value. Let's see, 0.89, that's high. Here I got a probability of 89%, and then the inverse cumulative distribution function accepts the probability as an input, and you can see in Excel I'm using norm inv. 89% is the parameter, and then it's returning for me the quantile of 1.225. That's the quantile. In the case of the normal, we would call that a z value. And what does the 1.225 mean? Well, as the quantile, then it's on the x-axis, somewhere right about here. I'm not going to be very exact. And I'm just going to draw a line up here. The inverse cumulative distribution function returned for me a quantile of 1.225. Meaning what? Meaning that the area under the curve to the left of that quantile is 89% of the area under the total PDF, by definition, which is 1 or 100%. So put another way, if this characterizes a random variable, then there's an 89% chance that this value will be 1.225 or less. Right? That's the value of the inverse cumulative distribution function. And so that is the meaning also of the CDF function itself, because if I take this quantile and go all, it's not a very straight line, could have done better there, go all the way up here, I'm going to hit this at 89%. See how that's what the CDF tells us? It's just a direct plot of the cumulative probability. Again here, 89% probability that the quantile or z value will be 1.225 or less. So I started with the inverse cumulative distribution function, but then now just to take a round trip back to where we started, then I'm right here, I have the cumulative distribution function. So you can see the notation here. The cumulative distribution function accepts the quantile, or in this case the z value of 1.225. In Excel I'm using norm dist, so these are inverse functions, and it returns for us the probability of 89%. Since these are inverse functions, by definition I had to get back to the 89%. So the cumulative distribution function tells us the probability that our value will be equal to or less than the z value that is the input. I'll share on the YouTube page the Excel here if you want to take a closer look, because you can change the location and scale of the normal here. So for example, we can take the standard deviation out to 2, and you can see it appears to be wider. It's still going to have a valid CDF, and then I've got an X value here that applies that so-called transformation on the standard normal, and gives us a new random variable. But the normal is also elegant in that it's what we call technically location scale invariant, or maybe it's scale location invariant. Can't remember exactly. And that means that if we take a standard normal denoted by z here and multiply it by some standard deviation value and add a mean, we transform it, change the mean and the dispersion, but we still get a normal. So if we multiply it and add, we still get a normal back. Okay, but I'm going to put this back to a random standard normal. And finally, just show you what I meant about, just a reminder about the nature of a continuous random variable. And again, this normal is a probability function that characterizes a continuous random variable, so that if we want to ask a question about a specific value, we really have to specify an interval. So for example, a really wide interval would be, what's the probability that the random value would fall between 1 and 2? So notice how I've got this plot, so it plots some lines here to carve this out. And so that's a wide interval, just to illustrate, but the probability that this random value falls between 1 and 2, to get that, then I've got a little bit of, okay, don't want that to show up, oh good. To get that really right, what we really want is the probability under the curve, within those quantiles, as a percentage of the whole one. And to get that, you can see what we really do is subtract. The easiest thing to do is subtract the CDF take the CDF for the 2, right? Because that's all of this area, and then just subtract the CDF for the 1, because that's all of this area, and the difference will give us what's left over. So in this case, that would be 97.7% approximately, because for the 2, we have 97.7% of the area under the curve to the left, and then we subtract the 84.1% that's to the left of the 1, and we get what's left, which is 13.6%, and so that would be the probability that the z random variable falls between 1 and 2. And so again, we can't really in a continuous random variable, we can't really specify the probability that a value is exactly equal to 3. We have to really do something more like, say, if we what's the probability that it's between 2.9 and 3.1. Okay, so then back to recapping the 3 key terms that I wanted to illustrate. And again, remember, we're looking at a continuous random variable. The first key term is the probability density function, the lowercase pdf here in green. The second term is the cumulative distribution function. It's the integral or antiderivative of the PDF, and it tells us the probability that the random outcome will be some value or less. And then the third term is the inverse cumulative distribution function, also called a quantile function, that accepts as a probability and returns for us the corresponding quantile or value. So that's the normal distribution as an instance of characterizing a continuous random variable. And then just below that here, also on the sheet, of course, I have, I thought I would just quickly show the simplest, or this is the second simplest discrete random variable that I can think of. The simplest would be the binomial, and then the second simplest, in my opinion, is the Poisson distribution, which is discrete. The Poisson is nice because it only has one parameter, lambda, which is both its mean and variance. So I have here a mean for the Poisson of 3. That means its mode is at 3 and also at 2. The mode of a Poisson is it's lambda and also it's lambda minus 1. So you can see it peaks here at 3 and also a little bit before the 3. But otherwise, a lot of similarities with one or two key helpful differences. In the case of a distribution that characterizes a discrete random variable, we have the probability density function also here in the case of a discrete variable. But notice here, I can plot this with what looks like a histogram because it's discrete. And so this is a key difference. For a discrete random variable, these values are intuitive because, in fact, so here happens to be the PDF. I said PDF, but I meant I should say technically PMF. A lot of people use PDF for both, but the PMF is just the PDF it's a probability mass function in the case of a discrete random variable. So with essentially the same meaning. So for the Poisson distribution, here is the probability mass function, and it's called a PMF, has a slightly different name because this is, after all, intuitive actually. The PMF does give us in this case, the probability of the outcome itself, because unlike with continuous random variable, discrete by definition, discrete variables, the way that I like to think about this is that continuous random variables must be measured, but discrete random variables can be counted. So like a die, or in this case like a Poisson, the probability that the outcome will be 0 or 1 or 2 and not something in between, not some real value or ratio value. So here in the case of what's the probability that the value is 3, we have a discrete value with a PMF, and that value is about 22%, which is telling us that there is a 22% that the outcome of the random variable will be 3. So you can see, unlike in the continuous case, for the discrete random variable, the PMF is immediately helpful to us. Okay, but we also do have the cumulative distribution function here in blue, and I've plotted it with dots to connote the discrete nature. And I just didn't take the time to figure out in Excel or how to show it properly, which is that properly it would be a step function, right? So it'd be something like this. But you would see that that would still convey the discrete nature of the random variable. And so, but as a CDF, that same test applies, right? It's bounded by 0% and 100%. And then finally, we also have the inverse cumulative distribution function, aka Quantile function, as before. And so just in this case, I generate, as before, a random variable. This could just be P. I have the random variable of 87.8%. And then I have the inverse cumulative distribution function, takes that probability and returns for me the quantile. But in this case, it's going to be an integer value consistent with the nature of the Poisson. And by the way here, Excel does not have a built-in inverse cumulative distribution function for the Poisson. So I've used this from Real Statistics. I'll put the link on here because he's published a very neat free package with some functions like this that are otherwise not available in Excel. So you can see for 87.8%, the inverse cumulative distribution function for the Poisson returns a 5, and that means right here at 5 we have the 87% falls in here at the fifth quantile. So this gives me a way then to generate random outcomes according to the Poisson just by running the random uniform values, and in each case I get the associated random Poisson, and we can close the loop by computing what is built into Excel, the Poisson distribution, Poisson distribution, yep, takes the X value, then my mean in this case is 3, and true for the CDF. So this is the associated cumulative distribution function. And in this case, I won't get the exact value back, but you can see that's because this inverse cumulative distribution function is finding the probability that is less than or equal to the associated CDF. So you can see over here, 2 is at 42%, 3 is at 65%, so 55.8 falls between 2 and 3 and really falls within this bin that characterizes the value of 3. So really we're getting P equals F of Q as the CDF. And that is the similar example for the discrete random variable. Thank you very much.